most people showed up at least, I think. So I think we can start. So first I would like to thank the organizers a lot for inviting me here to give this lecture. And I also hope that everyone will feel free to ask questions and interact. Also, during making this lecture, I also learned some stuff myself, so yeah, feel free to ask any questions if things are unclear, or if you want to know more. Okay, so let's quickly start with the plan. Given that this is quite a long lecture, I have it in the first part before the break, and the second part after the break. And we might plan some in-between breaks if I run out of slides. So for the first part, I really want to talk about lattices. And we start with some lattice theory. So what are lattices and what are the hard problems that we use in cryptography? Then I will give some intuition on how we build cryptography with these things. And how you build like encryption and signature schemes. And then we will do a bit of cryptoanalysis, which personally is my favorite part, where we try to see, okay, what are the best algorithms that we have to solve these problems. Okay, and then in part 2, I will introduce the lattices that we actually use in cryptography. We have to choose some family of lattices to use. And these might be familiar terms like CIS and LOE. And I will explain a bit how the security proofs then go in these schemes. Then I will also discuss some hard introductions that we have in lattice-based crypto, which kind of gives us a lot of confidence in these families of lattices. And then we finish off with a bit of algebraic lattices, which are used to we add some structure to make things efficient. And I have to give some acknowledgements because this last part of the reductions and the algebraic lattices is not really, I know it, but it's not really my expertise. But luckily my colleague Alice Bellemery was so kind to give me her slides and make me adapt those a bit. Okay, so yesterday we learned about codes, and Alex already said codes and lattices are kind of the same thing. So I thought of let's start with a slide, like how do we go from codes to lattices? What are the similarities, what are the differences? So both of these are just discrete additive groups. And just abstractly, they are kind of the same thing. For codes, this discreteness automatically comes because you're working over finite fields. For lattices, we'll see you get this discreteness in a slightly different way. They also have very similar problems, like finding short or close lattice points or code words. So yesterday we saw in Lattice that you would take some code word, add a bit of an error, and removing this error was the hard part. Well, we have something similar in lattices, where you get a point and finding a close lattice point is hard. So now some of the differences. How do you translate this from codes to lattices? Well, first in lattices, in code, we really like to use the Hamming distance. Yesterday we saw this over the binary field, but more generally you can do this over FQ to the n. And in lattices, we really love the Euclidean distance. Of course, in both worlds, we're not necessarily forced to use these measures of distance, but they are the most common one, and also give us a lot of tools there. And what I personally like a lot about the Euclidean distance is that it allows us to make pictures. So throughout this talk, I will show lots and lots and lots of pictures that hopefully give you a lot of geometric intuition. And so what's another thing that's different from codes, and Alex already mentioned this shortly yesterday, is that for codes, for this Lattice crypto system, for example, you really need this magical Gopa code in which you get the code. So you need some family of lattice, some family of code in which you can get the code well. But for lattices, we are a bit more free. We can essentially take any lattice, and as long as you have a particular good representation of it, some also called a short basis, then you kind of get this decoding for free. So you have way more choice in what kind of lattices you want to use. And then finally, which is kind of the most important one, in the world of codes, we always use row vectors. In the world of lattices, you always use column vectors. And this is a very decisive topic between the fields. I think this might be the one reason that they are not merged yet. But, so from now on, you will use column vectors. Okay, so let's start with what is a lattice. So, like I said already, it's a discrete group, and in our case, we will really focus on discrete subgroups of R to the n. And in R to the n, we have our Euclidean, standard Euclidean distance. So, what is discrete? Well, that means that for every point in our lattice, we can draw some open ball around it that does not contain any of the other lattice points. So, here we have an example with almost one of the most simplest lattices that we have, namely the integers inside of the reals. And of course, around every point we can draw some ball that does not contain any other integer points. Of course, in this case, in one dimension, a ball would more be like an interval, but for the picture I drew two-dimensional. Okay, and so we discussed the discreteness, and of course we have this additivity. So here we have a two-dimensional lattice, and suppose we have two lattice vectors, then we can always add them, or we can take, more generally, we can take any integer combination of these lattice vectors, and these will lie in the lattice again. That's just because it's an group. Okay, so now we can talk about some geometric properties of lattices. So from this discreteness property, we get that around every point we can draw some ball. But if you look closer, then every lattice point is essentially the same. Because of the additivity, the neighborhood of every point is essentially, exactly the same. So what we can do is just draw, let's say, the largest ball that we have. We can draw it around every point, and we know that it won't overlap with any of the other lattice points. Which means that instead of looking at all these points, we can just focus on one point. And now we can see, okay, let's try to make this ball as big as possible, such that it does not contain any other lattice points, or let's say contains the first other non-zero lattice point. And this distance that we then get is what we call the first minimum of a lattice. And there are two ways to look at this. So first we can say it's the minimum distance between any two distinct lattice points. And just like we had with codes yesterday, we can also say it's the length of the shortest non-zero vector. And this is equivalent. And now we go on to the second property, and that's the volume of a lattice. So the volume of a lattice is like we can draw some fundamental area with respect to the translations by the lattice, so you get kind of this tiling of the space. Oh, I see, by the way, that all my gray colors drop out on the screen, but you can see it on the other screens, hopefully. And this volume, because it gives a tiling of this space, this is what we call the volume of the lattice. And essentially, this is inversely correlated to the density of your lattice. So if we kind of have one lattice point for each piece of volume here. So the density of the amount of points in the space is kind of 1 over this volume. And of course, it doesn't matter which fundamental area we choose. We can take this one, for example. We can take this one. We can also take a completely different shape. But what we know is because they are all of fundamental area, they must have the same volume. So far I've been talking about like full rank lattices, which are like we have work in a two-dimensional space here, and the lattice also spans a two-dimensional space. More generally, it can be that you have, like your lattice has a smaller real span than the full space, and essentially what we do is just restrict to this real span and then do the usual thing. So officially you would have to adjust this definition a bit to say, okay, it's the co-volume of the real span of the lattice quotient out by your lattice. Okay, but I think like in the rest of the talk you can just assume everything is full rank and keep that in mind. Yeah.
I can also have a situation where you have, so let's say my lattice is has a one real dimension, but it has multiple integer dimensions, right? Because they have a strange name.
Yeah, so that's so you can prove that this exactly does not happen because of the discreteness. So if you would have, like, for example, you look on one line and you take all the integer combinations of like 1 and pi, for example. Then they're like independent in some sense over the integers, but not over the reals. But if you have this, then you can show that you can like get points that are like arbitrarily close to each other, and this isn't possible with the discreteness that we have. So that's indeed like something I crossed over, but yeah, that's what we get from this. So that's precisely kind of we have this minimum distance, which is bigger than 0. And, this allows those cases. But good question. Okay, so how are these two? So we define this minimum distance between lattice point, and we define this volume, which kind of is a density. So this minimum distance is kind of a local density, like you want to know how close your points are, and this other is kind of a global density. So you would expect that these are somehow related, and that's given by Minkowski's theorem. And the way I phrased it here is kind of makes it easy to see the proof. What we can do around every point that we have, we can draw a ball that is a half times the minimum distance. And because it's a half times the minimum distance, we know that any two of these balls cannot overlap, or at least like a bit maybe on the boundary, but not in terms of volume. So what we know is that these balls form a backing in this space. And what we also know, because this is that the volume of this ball must be bounded by the volume of this lattice, because we still have like some surrounding space that we did not use. So what we get is that the volume of this n-dimensional ball with radius half times minimum distance is bounded by the volume of the lattice. And now we can simply rewrite this, and what we then get is that the first minimum of the lattice is at most 2 times this normalized volume of the lattice divided by the normalized volume of this n-dimensional unit ball. And you can kind of assume that this is about square root n times the normalized volume. Okay, so far we have just talked about lattices, and we haven't introduced any way to represent them yet. Like we could say, okay, store all these infinitely many points, but that's not so feasible. So we do it in the same way as for codes. We define some bases or some generator matrix, you would say there. So we have some bases of R-linear independent vectors, and that's where we also exclude those cases where you get these like 1 and pi, for example. And the lattice consists of all the integer combinations of these basis vectors. And what we can do with such a basis is that we can also, for example, define this fundamental parallelipiped, So that consists of, we take our basis and we multiply it by the interval 0 to 1 to the n. So we get kind of the parallelepiped spanned by our basis vectors. And because this is a fundamental area, we can always, you see how nice of a tiling it gives. We know that the volume of your lattice is given by the volume of this fundamental parallelepiped. And then we have some kind of basic linear algebra that says that this is equal to the absolute value of the determinant of this basis. And here I'm very much assuming that this basis is square and that we have a full lattice. You can also define it properly if you don't have that. Okay, but this is just one basis of a lattice and one way to represent it. But in fact, we can have infinitely many distinct bases as long as you are in dimension 2 or higher. So here we have another basis of exactly the same lattice. And this is something that we're really gonna use, the fact that we have 2 ways to represent the same lattice. And of course, again, I can draw the fundamental parallelepiped of this basis, and you see how kind of distorted and not nice it looks. But it still has the same volume. Okay, so what kind of hard problems do we have in these lattices? And I must say, like, all these problems don't look very hard in 2 dimensions, especially because I'm drawing all the points already. But you must imagine that normally you don't get any of these points. You just get some kind of basis as input. So you get n vectors, and it's a lot. It's not so easy to even draw these points. I will try to give a bit more intuition on this later. Okay, but what problems do we have? Well, we define this first minimum, which is the length of this shortest non-zero vector, and of course, then the first question is, okay, can we find such a vector? And this is called the shortest vector problem. Okay, and then secondly, we have this kind of decoding problem that we also saw in Lattice, is that given any target in the space, so in the real space, find a closest lattice vector to it. And this is what we call the closest vector problem. Okay, and what's important about this problem is that they really become hard once you increase the dimension. So, and this is even like with a quantum computer, which is very important, of course, for our post-quantum crypto. And so, more precisely, the best algorithms that we have, they take exponential time in this dimension. So they take 2 to the power some constant times n. And classically, this constant, the best that we can do is 0.292. And quantumly, this is about 0.265. So what we also see is that this constant for the quantum regime is only a slightly bit lower than what we have for the classical part. So we don't get this crunch speedup that we saw yesterday, where you get a square root speedup, which would mean that this constant will be divided by 2. So that's also really something that is nice, at least so far. Let's really seem to be very secure, also against quantum computers. So this is in theory, but what can we do in practice? Well, NS2, again, I've already drew the picture of it, is very easy and very efficient in practice. Up to like NS60, NS80, we now have software that can do this quite fast, in a couple of seconds, few minutes maybe. Now, the records go up all the way to, I think it's now 186, and this really involves like a very big computer with multiple terabytes of RAM and multiple GPUs that compute for multiple weeks, and then we find this one teeny tiny short vector. And what are we using in cryptography? Well, these are really lattices of dimension like at least 400, but even to 1,000. And if you roughly do like the computation of like 0.292 times this 400, you kind of get around this 128 bits security. Okay, but these exact versions of the problem, so finding...
It wasn't the previous one. You kind of merged the two problems together in the complexity. Is it because it's exactly the same algorithm, or the algorithms have a comparable complexity and you also have a reduction between the two?
It's essentially the same. So in theory, it's always a bit, like in terms of provable reductions, it's always a bit harder, but in practice concretely and let's say heuristically, they are the same to solve. Yeah, we'll come back to that a bit later also. Okay, so but these are the exact versions of the problem, and those are not the one that we really use in cryptography. We need some kind of, we have some lenience. So we have some approximate versions of these problems. So instead of finding a shortest vector, we are fine with finding one that is not too long. So let's say some alpha times lambda 1. By the way, how you define these precise, like approximate relatively to what, is also kind of a heavy debate of what's the most nice way to do this. What you could also do, for example, is we have this Minkowski bound. So we know that if we take this Minkowski bound, we know there exists a vector that's short enough that we can find. And also, if we go back, this Minkowski bound is actually efficient to compute. Like we can compute this volume. So you could, if you find a vector, you actually know it's less than this Minkowski bound. So you could also say we are going to define this approximation relatively to this bound. So we say alpha times something that's short in alpha times this Minkowski bound. Okay, but this is for SCP, and of course for CVP we can also say, okay, we don't want to find the closest lattice point. We just want one that is somewhat close enough. And surprisingly, this is still seems very hard to solve when the dimension is large, and when these approximation factors are of polynomial size. Once we go to like exponential approximation factors, then we can do things efficiently, but as long as these stay polynomial, then asymptotically, it's still very hard. Okay, and we now saw these approximation versions, but we kind of also have a different version, namely the promise version, where we get promised that our lattice contains a very short vector, like one that is way shorter than what this Minkowski bound indicates. And in terms of a picture, what you kind of get is that you get this lattice that is kind of very dense in at least, let's say, one direction. And it turns out that this is easier to find also. So just like we have the approximation, if you get promised that a lattice contains an unusually short vector, then it can be easier to find. And on the other side, for the decoding, and this one is a bit more intuitive why it's easier, if we get a promise that our target that we had lies exceptionally close to a lattice point already, it's easier to find that lattice point. And this problem of like this, we call also the boundless distance decoding problem, in this you get this promise that it really lies close to your lattice. And this is expressed in some parameter delta that is, yeah, let's say at most a half, but often much smaller, let's say like 1 over square root n or things like that in crypto. And I say they are easier, but in fact they are still like, they're easier than the exact problem, but they're still hard to solve when this dimension is large and when this promise, this delta factor isn't too small, so when they're not too close to the lattice. Okay, so what is this? I already talked a bit about this, but you can make some nice trade-off between the approximation factor that we have and the best algorithms, the best time complexity that we have to solve them. And on the approximation side, we see that if we have a polynomial approximation factor, like I already mentioned before, the best algorithms that we have are still of exponential time. Now, if you would go to kind of a sub-exponential approximation factor of like 2 to the O of square root n, then actually we can also find these solutions in about 2 to the O of square root n. And lastly, if we go to exponentially large approximation factors, then we actually have polynomial time algorithms to solve this. And this is something I will get back to in the later part of this part 1 of the talk. And the nice thing is that we have some kind of, let me first mention this, of course, we want to have exponential hardness, so cryptography really lies on this, this thin bar on the left where we have small polynomial approximation factors. And these promise versions of the problem, so we have this unusually short SUP, and we have this bounded distance decoding problem. On that side, the picture kind of looks exactly the same. But now, of course, we have like some minuses here in the exponents. So if we have a promise that it lies within like a factor like 1 over something polynomial towards the lattice, then it's still exponentially hard. If this becomes exponentially small, exponentially close to the lattice, then it's easy to find. And there are deeper reasons why this is so symmetric. Especially for certain family lattices, you really have good reductions between these. Also, in general, you have some reductions which are often quantum reductions, but yeah, it's really well understood that you have this kind of duality between these problems. Okay, so a quick recap of this first part. We have seen that lattices are discrete subgroups of the real space. We have seen that lattices can be efficiently represented by a basis, so we have these infinitely many points, but we can represent them just by a few vectors. And we have seen that for large dimensions and small enough approximation factors, all these problems are hard. Like we have this finding these short vectors and finding closed vectors. And I didn't really go into this, but there are, of course, many more variants possible to how you state these problems. So now we have talked about kind of the search versions of these problems. You really want to find this lattice point. But of course, you could also say we have a decisional version. Like we want to decide if a target lies close to the lattice or not. We want to decide if a lattice contains an unusually short vector or not. We can also talk about one or more solutions, like now we agree also for one solution. You can also say, I don't want to find a short vector, I want to find a full basis that has somewhat short vectors. And okay, so we have now all this theory of lattices, we have these hard problems. So how do we turn this into cryptography? Okay, and what's very important and kind of the fundamental thing that gets used a lot it's kind of the fundamental idea behind lattice-based crypto is that we can make this trapdoor between a good representation of your lattice and a bad representation of your lattice. And when I say good, I mean I want to have a basis that consists of short vectors that are also somewhat orthogonal. And actually later we will see that this is somewhat related. Like when the vectors are short, they are also very orthogonal, and the other way around. And on the other side, we have this bad basis of vectors that are somewhat long and also not so orthogonal. And like intuitively, because this shortest vector problem is hard, finding short vectors is difficult. Going from this bad representation to this good representation is difficult. And maybe it's easier if I remove the points to get a little bit of more intuition of like why this becomes like why we find one a good representation and why the other is bad. Well, on the left we have this nice almost orthogonal basis, and I think most of you can maybe like see in your mind, okay, what kind of lattice we get from this. If you try to do the same on the right side, it's not so clear what you get. That's the kind of the intuition. Of course, in higher dimensions, this becomes, 3 dimensions is nice, 4 dimensions, well, that's kind of the limit, and then beyond that, it's hard to imagine things sometimes. So the idea is then we have some key generation process that gives us some random lattice, like Alex already mentioned yesterday. We really need this, or I think maybe it was get ready earlier, but like that we need randomness in these schemes. So we want to generate some random lattice along with such a good representation. And this is precisely where the maybe familiar terms like n-true and LB and cis and all these things come in. But for now, I will just assume we can do something like this, and all these n-true and LB and cis, they will come in the second part of the talk. And just to clarify again, like why do we need a random lattice? So if it's not random, if we just have some fixed lattice, then I guess everyone has, if we can make a good representation for it, then everyone can. So we need some random lattice. Okay, so what can we do with such a good representation? Well, we can, for one, like decode with it. Here is like a very almost trivial algorithm. Suppose we get as input some target, and we can write that in terms of our bases. So, for example, this is like minus 1.4 times the first basis vector plus 2.2 times the second basis vector. Now, a lattice vector must have integer coordinates here. So what's the most simplest thing we can do? We just round these coordinates. And so here we get like minus 1, and here we get 2. And what we then get, in this case, this example is this lattice point, and we see indeed that this is the closest lattice point. So this is something that was supposed to be hard, like decoding, but with this good basis, we seem to be able to do just that, like the decoding. So what can we say about this error that we get between this target and this vector? Well, we know that because we rounded the coordinates, we know that the difference must be between minus 1/2 and 1/2. So we get some error that lies in our basis multiplied by this minus 1/2 to 1/2 to the n. And essentially this is precisely this fundamental parallelepiped that we saw earlier, but then like translated to the center. So we always know that we get an error that lies in here. And in this picture, okay, so you cannot see it here so well, but still in every box that we have, any point that lies in there would get decoded to the lattice point that lies in the center of it. So what is then the decoding, like what kind of approximation factors do we get, and how good can we solve these bound distance decoding problems? Well, for the bound distance decoding problem, for us to decode this point well, we must look at the inner radius of this fundamental parallelepiped. Because if we know that an error is smaller than this radius, then we know it must lie in this fundamental parallelepiped around 0, and we know that it will be decoded well. Now, in the other direction, if we just want to find a somewhat close lattice point, well, the biggest that our error can be is if it kind of lies somewhere on the outer radius of this fundamental parallelepiped. Okay. And what we see also, when I show you the same thing with a different basis, is that the better the basis, the closer this solution. So here we have this almost orthogonal basis, so we get this almost kind of square, you have to mention a bit, almost square fundamental area, and as a result, this inner radius is quite large, and this outer radius is relatively small. If we do the same thing for a bad basis, we see that this inner radius becomes like super small, and this outer radius becomes extremely large. And of course, these are like worst case bounds, but also you can prove that if you just get a random target, for example, that these bad bases behave way worse than these good bases. Okay, so what we have seen is that with a good basis we can decode, with a bad basis we can still decode, but only at very, like for errors that lie essentially close to the lattice or give us a very far away lattice point. So from this we have already enough ingredients to build an encryption scheme. Not so surprisingly, we start with this key generation where we get our secret key, which is a good basis, a good representation of this lattice. And we have our public key, which is a bad basis of this lattice. And how do we encrypt something? So someone else takes sees this public basis, and what this person does is they take their message and they encode it as some lattice point. I will not go into detail on how to do this now, but they can do this with the public key because they have a basis of the lattice, so they can encode something as a lattice point. And now, just as in Lattice, we're going to add a little bit of error to it. And then what we send over the wire is this noisy message. Okay, so how do we now decrypt this? Well, we start with this noisy message. And of course, if we know our good basis, then we can, and this error is not too big, we can decode it. And note that this error that we added, we can control it ourselves. So this is really a bounded decoding problem. We get a promise that this error is not too large, and then we can, with a good enough base, we can decode it. And of course, what we assume for this, for it to be secure, is that we cannot solve this bounded decoding problem if we only get this bad basis. And I hope that intuitively that's kind of clear why we cannot do that. And just in the example here, for example, if we would decode with this bad basis, we won't get this nearby lattice point, which is the message. We get this far away lattice point that does not coincide with the message.
Do you mean if you decode using the algorithm that you showed before, by just rounding the...
Yeah. Yeah, just with that very simple algorithm, you can build this encryption scheme.
Is the wrong message that you get, is that still similar to the original message?
I mean, that depends a bit on your how you encode things, of course, but essentially, I mean, it's still going to be somewhat close to the good message, depending on how bad your bad representation is. So, but essentially, what you will get is that this is, for example, like, okay, what you could say, we take a basis that has exponentially, like vectors that are exponentially longer than your first minimum, and in that case, this message would also be like exponentially far away from the good message. In practice, we don't want to do that because exponential is quite large, and we don't want to have such large vectors to write down. But that's essentially the idea.
A few slides before, you said that you have to generate a random lattice.
Yep.
What do you mean by random lattice?
That's a very good question. So you can actually define like a random lattice, as in you take the whole space of lattices and you can define some measure on that, and then you can get a random lattice. In practice, we don't want to do any of this. And so we want to have like, easier ways to define to sample a somewhat random lattice, some random family of lattices. And later with this LOE and SIS, that's precisely kind of what we do. We fix some family of random lattices and we show how to sample from it. And this turns out to be in the end kind of similar to what we do in codes. Like these lattices are very much like kind of codes, but then for not binary but higher modulus Q. And in this regime everything is finite, so we can just kind of sample uniformly and is okay. But I will come back to that in the second part in more detail. But that's indeed like what is the notion of random lattice. When you see someone write a random lattice, it's either the very strict mathematical one, or it's more, let's say, heuristic of, okay, it looks like a random lattice, or things like that. Okay, so now we have done encryption, so let's also just do signatures. We start with the same thing, good basis, bad basis. So this is what we call a hash and sign signature scheme, and that's precisely because of this part. We take our message M, and we apply some hash function to it to get a target that lies somewhere in our space. And as a signer, I have access to the secret key, to the good basis. And I'm going to use this to find a somewhat nearby lattice point. And this is going to be my signature, this nearby lattice point. And so what I'm kind of doing here is I'm kind of proving that I can find nearby lattice points in this lattice, and me being able to do that means that I know the secret key is the ID, which means that I'm the proper person that's allowed to sign these messages. Now, how do we verify this? Well, we have our public key, so we can check that this point that we get is actually a lattice point. We should definitely not forget that part. And we can check if it's close to this target. And that's it. So what would we have to do to forge a signature? Well, we would have to find a nearby lattice point, and essentially our assumption is that with this batch representation, it's hard to do precisely. Okay, so we have now seen encryption signatures just from this good basis and this very simple decoding algorithm. There is one problem with this signature scheme, though, is that every signature that we get, because of how we have built this decoding algorithm, if we take our target here and we get some signatures on that point that's close to it, and we know, we've seen before, that the error then lies in this fundamental parallel pivot. Now, if we get many signatures, not just one, so we get like one here, so we get another error in this fundamental parallel pivot, and suppose we get many signatures. Then we get all these points that are kind of spread out uniformly over this fundamental parallel pivot. And in some sense, this parallel pivot is directly linked to our secret key. So what we're seeing here is that our signatures are kind of leaking information about our secret key. And in fact, this is what, like, for the first lattice-based signature schemes that we have had, like GGH and entry sign, they were broken essentially because of this. You can, from these points, you can learn the shape of this parallel pivot essentially, and from that recover this short basis or this secret key. So we need to do one more thing to kind of prevent this. And the idea is that so I have to talk loudly for a second. So the idea is that we will, instead of solving this with this rounding algorithm that's very deterministic and gives you all these points in this parallel pivot, we're going to try to solve this approximately to be randomly. Make sure we don't leak any information about our. And kind of the adaptation that is kind of simple, but kind of still hard to do in implement in practice, is that instead of returning this nearby lattice point with this decoding algorithm, we define some distribution that kind of lies around this target, and this will be the discrete Gaussian distribution, but I won't give much more details around about that. But what you kind of get is what you can do with this good representation is actually sample from this distribution around this target. And this distribution is kind of just depends on your lattice. It does not depend on this secret and good representation. So if you just get samples from this distribution, it does not leak any information about your secret key. But still, this distribution is built in such a way that the lattice points you get are somewhat close to the target. And then, of course, the verification works the same way. We check if it's close. And if you do this properly with the right distribution, then you can probably show that your signature does not depend in any way on your secret basis. And if you look, for example, at the Falcon signature scheme, that's precisely this, like this idea of using these discrete Gaussian distribution around your target, plus and the keygen using entry lenses, which I will get into later. And this is also precisely, by the way, why Falcon, like, it got standardized, but there's also dilithium that got standardized along with it, because Falcon is actually quite, I guess Bas will talk about this tomorrow maybe, it's quite hard to implement, because the sampling is really something that is very hard to do in constant time, and also if you want to mask things later in your hardware. So it's quite complex under the hood, but the idea is very simple. Okay, so let's give a short recap on what we've seen. We have seen that from the hardness of this bounded distance decoding in some family of random lattices that I didn't specify further, we can get an encryption scheme if we have this key generation of getting a good representation of it. Secondly, if we have this approximate CP that's hard, then from this we can build a signature scheme. More precisely, we need to be able to do this kind of sampling, but I will just ignore that for a bit now. And yeah, as already said before, what kind of families of lattices we put in here, that will be discussed in part 2. Now, lattices can do much more than just encryption and signatures. For example, what we can do is like fully homomorphic encryption, which is something where you can encrypt your data and still let someone else compute on your data. And then in the end, you decrypt it yourself and you get the result. And that almost sounds impossible, like it's an impossible thing, but using lattices, you can do it. You can also do identity-based encryption, and you can do like functional encryption for linear functions, and way more. So what we will now get into in the last part before the break, I'm thinking, do people want a break, or do they, are we fine with continuing? Yes? Okay, good. Then the last part that I want to dive into before the break is how hard are these problems precisely, and what are the best algorithms that we have to solve them. So let's do some cryptanalysis. So we have seen this picture before of the kind of the rough trade-off that we have in asymptotic complexity, and I will discuss a few parts of this. Namely, first, the exact CVP case, like or SVP case in this case. How do we solve that? Well, that's what we use so-called lattice sieving algorithms for. Then on the other end of the spectrum, where we have this exponentially large approximation factor, we have the LLL algorithm that runs in polynomial time and allows us to find these factors of that large approximation. And I will very shortly get into this BKZ algorithm that kind of gives you the full trade-off curve between these things. And by the way, the other side of this promise side, the same algorithms apply there too. It's just a bit harder to see why that happens, so I will stick to the approximation side. Okay, so let's discuss lattice sieving. And for this, I first want to talk about heuristics. If you go to lattice-based cryptanalysis, there are heuristics everywhere. And that the reason for this essentially is that we don't know how to get the results we want without using any of these heuristics. And with these heuristics, we can actually get close to what we can do in practice. So like the analysis, the heuristic analysis gets close to our practical algorithms. If there are any people that like proofs, then this is, I think, still an area that is closing this gap between provable lattice algorithms and heuristic algorithms is really something that I think there's still a lot of improvements possible. And also these heuristics allow us to reason about the practical behavior of algorithms in a often much simpler way. And maybe also the most important almost for instantiating cryptographic schemes is we cannot only derive the asymptotic hardness of the problems like the exponential, the complexity statements we have seen with big O notations and whatever. We can often also get very concrete hardness estimates. So we have some instantiation of our problem, we have our best algorithm to solve it with our heuristic analysis, and we can say almost precisely plus minus, let's say, 5 to 10 bits. This is how long it's going to take to run this. And that's important if you want to choose parameters for your schemes. You don't want to pick too big parameters just because you're insecure about the analysis. Another way to view this difference between provable and heuristic is that in the provable regime we really are often talking about worst case analysis. Like we want the provable algorithm must solve these problems in the worst case. On the heuristic side, it's often much more about the average case of a problem and then simplified, essentially. Okay, so why is this okay to do for lattice problems and for attacking these lattice problems? Well, it turns out that the average case is often actually the worst case in lattices. And again, I refer to part 2 for more details on this. And also because they just match very well with what we do in practice. So that gives us a lot of confidence about it. So let's start with the most important heuristic that we have. And that is essentially that this global density that we have, given by the volume of your lattice. So this essentially says how many points there are in a given area of space. This Gaussian heuristic says that the amount of points that we expect in this area is also roughly the amount of points that we get in this area, very simplistically stated. So if we get some nice volume, so let's say some large ball, then given this density we can compute how many lattice points you would roughly expect in this. And it turns out in practice, if your lattice is kind of random enough, that this is very close to the actual amount of lattice points that lie in there.
So if you just scale up the ball to infinity, this is true, right? So
yeah, so if you scale it up to infinity, it's true. Essentially, the heuristic says, okay, we can pick also smaller shapes and things, and it's still true. In theory, you can prove even more. Like if you take any such shape and you would look at the expectation of the amount of lattice points in there, if you would just move it around uniformly, then this number, this volume of the thing times the density, is precisely the expected number of lattice points in there. And also, and this is a bit depending on your shape, but if you for random lattices under this really mathematical definition of random lattices, we can also prove similar statements in expectation, but also often in kind of some density arguments that it's almost always the case. But what's important for us is that this is very much true in practice for random lattices, and this has been verified experimentally quite a lot. And here I'm using the word random lattice again. I want to stress that this is really a very weak heuristic notion of random lattices. Kind of anything that we don't see any additional structure, and immediately that is often behaves like random. Okay, this is a slide that's I'm not really going to use the results from this, but I just want to kind of give you some intuition about this very high-dimensional geometry. I guess most people are not used to necessarily working in hundreds of dimensions. And things can behave a bit unintuitively in those high dimensions. So for example, if we take a box between like -1 and 1 to the n, then you can compute this thing as volume 2 to the n. Like it has, the width is 2, so for every dimension we add an exponent. But if we look at a unit ball, so this is a unit ball of radius 1, so it's also like 2 in total in terms of width. And this thing actually has a volume that goes quite quickly to 0. So just in terms of pictures, I mean, this is, of course, I cannot draw in these high dimensions, but essentially what we get in dimension 2, we see that this ball takes up like most part of the box. But in higher dimensions, high dimensions, we're just talking about dimension 10 here, it has already almost disappeared. Which is strange because technically this ball will still hit this border and will still hit this border, but it also kind of disappears. So it's some very unintuitive things that you get in these high dimensions. Okay, but I mean you can forget about this again if you want, but it's just some things. What's more important for us is that if you scale things in n dimensions, then the volume actually changes by a factor r to the n. And for large n, like these are exponential things, so it can make big differences. So suppose we have some 500 dimensional lattice, and we have some ball in there that has exactly the same volume as this lattice. So you would expect that there is around 1 lattice point in there, according to the Gaussian heuristic. I mean, I'm also fine if there are 10 in there or 0, but it's kind of a small amount. By the way, we forget for a second about the point 0, because we picked this ball in the center, so always 0 is going to be in there, but it's a bit of a planted thing. We can ignore that. Okay, so according to the Gaussian heuristic, we get approximately 1 lattice point in there in this ball. But now suppose we make the radius of this ball only 5% larger, which is, I mean, in terms of length, that's almost nothing. But suddenly then we have more than 10 to the 10 lattice points in this ball. So that's like, this kind of gives some idea about the huge number of these lattice points we have. And yeah, gives maybe some idea about the complications that you can have in these very high dimensions. And at the same time, if we look at, if we shrink the ball a little bit by 5%, then we see that the expected number of lattice points in there is, well, 10 to the minus 12, it's like almost 0. So if we shrink it a little bit, we don't expect to have any lattice point there, except this 0 in the middle. So what does this say about the first minimum of a random lattice? Well, we have this ball of this certain gamma with the ball has the same volume as this lattice. Well, actually, this gamma must then be close to the first minimum, because if we shrink a little bit, there are no lattice points in there. If we grow a little bit, there are exponentially many lattice points in there. And so what you could call this gamma, like we write this as like the Gaussian, the GH of the lattice, the Gaussian heuristic of the lattice. And which is this normalized volume of the lattice divided by this normalized volume of the n-dimensional unit ball. And you might have recognized this from earlier. This is exactly the same thing that we had in the Minkowski bound, except there we had a 2 in front of it. So what we see is that this Minkowski bound up to a factor 2 is essentially like tight for random lattices. So if we take some random lattice, then we expect that the first minimum is about half times this Minkowski bound, and that's what we call this the Gaussian heuristic of our lattice. So I also kind of try to give some idea of how these points are distributed in such a high-dimensional ball. Essentially, what you get is that almost all the points lie on the very close to the outer part, and that's something that is not in 2 dimensions. That's not the case at all. And yeah, so you have to think a bit differently. If you have any shape, it's often the border where all the lattice points lie. Okay, now let's do some lattice sieving to solve this shortest vector problem. So we have seen that these high dimensions can be a bit problematic, but what can we do? So the idea behind this algorithm is that we start with a list of lattice vectors. Generally, these are very long because we don't know how to get, we have a better representation, we don't know how to get shorter lattice vectors. And this list is very large. And what we then repeat is a very simple step. We try to find 2 lattice points in our list that lie somewhat close. And if we find them, we subtract them from each other, and by additivity we get another lattice point, and we insert that one back in our list. And maybe we okay, we can even replace, let's say, the longest of these 2. So that we don't, that our list doesn't grow. And then we just continue to do this, and if we have enough vectors in our list, we hope that kind of the vectors become shorter and shorter and shorter until we find a shortest vector or a almost shortest vector. So let's talk shortly about what the complexity of this algorithm is. Now, what I said before is we kind of assume that most of these lattice points, if we take some volume, most of these lattice points lie around the edge of it. And just for simplicity, let's assume that we start with a list of vectors that is bounded in length by some gamma. And I mean, if we just assume that these are kind of uniform vectors from this, we get this picture where they all lie on the border. So that's kind of the assumption we add to this. We assume that all these vectors have some uniform direction also, which I mean is quite a weak assumption, I would say. So we have some of these vectors in our list. So the question is then, what's the probability that we can find a pair of vectors that lies, is this like where the difference between these 2 vectors is less than this gamma, because we want to kind of decrease this radius. Now if we have, okay, this half by the way is only if you have like unit vectors, but if you have a lattice vector here in your list, then when does a other lattice vector lie close enough such that the difference is let's say about the same size or slightly smaller? Well, that is if the angle between them is about pi over 3, which kind of says that any lattice point that kind of lies in this sphere, like this spherical cap, gives us one of these kind of reductions, like these smaller lattice points. Now, if they are all kind of uniformly directed, then what is the probability that given one of these vectors we find another one that lies in this spherical cap? That's just given by the relative volume of the spherical cap compared to the complete volume of this sphere. And that's actually given by, like asymptotically given by this thing. So we have this 3 over 4 to the power n over 2, and then we ignore any kind of polynomial terms. And this epsilon here really depends on kind of this part here. Like if you make this slightly smaller, then you need to adapt this epsilon a bit, but let's just assume it's 0 for now. So this probability is exponentially small, which is maybe to be expected in such high dimensions. So how many of these factors do we need in our list to be able to kind of find enough new close pairs, new vectors, so that we can continue this process and not end up with an empty list, let's say, or don't find any new shorter vectors. Well, we have n squared pairs for, we want the new list size to be n again, or roughly n. And we know that the probability that any pair gives this reduction is given by this volume, so kind of about 3 over 4 to the n over 2. So we have the amount of pairs times this probability, and we need it to be at least n. And from this you can see that we need n to be not 3 over 4, but 4 over 3 to the power n over 2. So we need an exponentially many amount of factors in this list, and then at least with this very maybe a bit vague heuristic explanation, we can kind of continue finding pairs until we have very small vectors. So what's the space that we need for this algorithm? Well, that's essentially the lattice points, this list that we need to save. So that is this n, which is 4 over 3 to the power n over 2, which is roughly 2 to the power 0.2 times, oh, there should be an n here. Which is very large, and is really a problem in this algorithm, but oh well, it's the best we can do. And on the time side, well, what do we have to do? We have to, in every iteration, we have this big list of vectors, and we need to essentially check all the pairs. We take any pair of vectors in this list, and we check if they are somewhat close. So roughly you would need n squared number of these checks. They all take polynomial time. We also, for simplicity, assume we only need to repeat this a polynomial amount of time, which kind of is the case if you every time shrink by a little factor, it becomes smaller quite quickly. So we get this 2 to the power 0.415 times the dimension. Of course, this process of, okay, we just go over all the pairs and we check if they're close, is in some sense the most stupid thing you can do. That's, yeah, it's the most basic algorithm, but also not the most optimal one. And you can improve this further. And this is also where these locally sensitive, this nearest neighbor searching algorithms come into that I think were also mentioned yesterday by Alex. And if we do work smartly with this, then we can actually improve this down to 2 to the power 0.292 times n. And this is the constant that we also solved earlier to solve SCP. And then for the quantum algorithm, you kind of do some quantum search, but because these algorithms are quite complex, this quantum speedup that you get there is very, very little by Chrome. Okay. Any questions about this quite technical? Okay. Then let's now get into some base reduction. So we talked now about the exact case. We have some exponential time algorithm to solve it. Now let's go to the other side of things. And for that, we first have to define some more machinery. Namely, we define this Cron-Schmidt organization, where we take our basis, and we say that our first Cron-Schmidt vector is just the first basis vector. Now, for the second Cron-Schmidt vector, what we do is we take our second basis vector and we project it orthogonally away from our first basis vector. So we project it from here orthogonally to this part. And this is what we repeat. Like you would normally take your third basis vector, you would project it away from the first two basis vectors, the fourth one from the first three, etc. And what this gives you is, again, some kind of fundamental area, where we, again, do get this minus half and half, but then now instead of the basis, we have these Cron-Schmidt vectors in there. And in terms of a picture, you get kind of like this. And what's nice about this thing is that it's square, and squares are nice shapes that we can do a lot with. And this organization comes with some decoding algorithm that's like a little bit more advanced than this simple rounding algorithm that we had, but essentially it's not much different. What we do is we get our target, and we first try to make this target, like we try to move this target by lattice vectors until we get to some small error, and that's equivalent to actually finding your close lattice point. So let's try to move this target. Well, first we're going to look at the second Gram-Schmidt vector. We want to make it small in that direction. So what we can do is we see that it's like we could remove the second Gram-Schmidt vector 2 times. Like we go from here to here, and then it's nicely on this hyperplane, which is small in that direction. And to do that, we have to subtract our second basis vector 2 times. So we get our target, we remove the second basis vector 1 time, which goes to here if you remember what the second basis vector looks like. And we subtract it again, and we get a target that lies here. Now we know that in the direction of B2 star it's kind of small. Now we are going to do the same thing, but now for in the direction of B1 star. So we have our target that now lies here, and we can add another basis vector to make it here, and then suddenly it's in this box. So again, what we get, and then this also works for high dimensions, what we get is a decoding algorithm where you get some target, you look in which box it lies, and you get the closest, like the center lattice point in that box. And why we like this box so much, like this Gram-Schmidt organization, is that it's always kind of better than this simple rounding algorithm. And now let's have a look what this means in terms of this good and bad basis. We get the same picture again. If we have a good basis of things that are almost orthogonal, then what we get is that these Gram-Schmidt vectors are going to be almost the same size. So this box that we get is going to be very square. Now on the bad basis side, if we start with a very like non-orthogonal pair of basis vectors, then we can get this behavior that the first base vector is long. I mean, that's just the first basis. The first Gram-Schmidt vector is long because it's just the first basis vector. And the second Gram-Schmidt vector is going to be super short suddenly. So looking at this fundamental areas, we get this very square box here and this very non-square box here. And note that the sides of this box are precisely given by the length of these Gram-Schmidt vectors. Like the length here is precisely maybe it's easy to see here, the length here is precisely the length of this first Gram-Schmidt vector, the length of this side is precisely the length of this Gram-Schmidt vector. And the volume of this box is just the product of the lengths of the sides, so we get this product of the length of Gram-Schmidt vectors. And we know that this must be equal to the volume of your lattice because it's a fundamental area. So the product of all these Gram-Schmidt lengths is already predetermined, it's fixed. Which also explains that if the first one is very long, then the second one must be very short in this case. And because we want this box to be nice and square, so that our decoding works well, like this inner radius and this outer radius. Oh, by the way, that's what I have here, this inner, here we get the code well, here we get the code badly. We want for a good basis that all these Gram-Schmidt norms are kind of the same. That's what we could optimally get.
Sorry, I have a question about the algorithm. How do you know that once you reduce with one of the lattice vectors, you don't get worse in the other?
Okay, so that's precisely kind of why we do this Gram-Schmidt process, because by definition this second Gram-Schmidt vector here is orthogonal to all the ones before. So if we then we cannot go from the last Gram-Schmidt vector to the first. So any change that we make in the direction of this last constraint vector, they cannot change anymore by the first few base vectors because they are orthogonal to it. Yeah, good question. That's the idea behind the algorithm. Okay, so we want these constraint lengths to be kind of balanced. So we can make a plot of this. We can say now this is a log plot, so we take the log of these constraint lengths, so their sum is going to be fixed, which means in terms of such a plot, I see again that the red color kind of removed itself, but that means in this plot that the volume, or sorry, the area, not the volume, the area under these two plots, it must be the same always. And for a bed profile, that means that it starts with very large values, like we start with very large vectors and very large constraint vectors. But because its area is the same or is fixed, it must then drop down very quickly. So at the end, these constraint vectors must be extremely short. While for a good profile, we start with smaller vectors, and then these last constraint vectors are also generally larger. And remember that for this kind of approximate CDP, we care about the sum of these constraint norms, or the square constraint norms, and for this bounded economy, we care kind of about the smallest one, like this inner radius. So for the approximate, we kind of care about the total thing, but it's mostly dominated by the largest value here. And for the bounded economy, we care about this thing not being too small. So for this good profile, this good basis, we from this see that we can decode better. And this profile is something that we really like to look at because it kind of gives you, even though you have this n-dimensional object and this n-dimensional representation, this basis, it just gives a quick graph of kind of what is the geometry of this thing. So it kind of measures the length and orthogonality of one of these bases. Okay, now I can very simply define what we call base reduction, and that's essentially to go from one of these bed bases, bed profiles, that is very steep, to a good basis with a better profile that is much more balanced. So you could just say base reduction is flattening this profile. Now just let me quickly get like a very short example in there of how these things look in practice in schemes. For example, if we look at n-true, what kind of public and secret spaces these things produce. Then this public basis starts with very large vectors, and then at the end it's actually very short, so this is like things corresponding to norm 1. While the secret basis is like not perfectly, but almost perfectly balanced, which allows us to decode very well or solve the approximation, like the CDP problems, really well. Now, how do we do this reduction? And I will start with the simplest case. That's actually, I mean, this is just the two-dimensional case, and there we can do this optimally. And I like to call this the wristwatch lemma because, I mean, looking at the shape of this is kind of a wristwatch. And what it says is that for any lattice of rank 2, you can make a basis such that the first basis vector is at most as long as the second basis vector. So if we just assume, like up to rotation, that our first basis vector is this one, then our second basis vector must lie outside of this orange area. And secondly, we have that the inner product between these two base vectors, which essentially gives you a notion on their angle, must be bounded by this half times the length of the first base vector, which in this picture means that the second base vector must be in this green part. And if this second base vector is in this green part, then we see that it's quite orthogonal, and as a result we get some, I mean, it's a nice exercise to do, but if you take these two properties, then what you get is that the first Gram-Schmidt vector is at most as long as this small constant times the second Gram-Schmidt vector. The other way to look at this is that the second Gram-Schmidt vector is lower bounded by some constant times the first Gram-Schmidt vector. So the second Gram-Schmidt vector cannot be much shorter than the first one, which means that this profile, this simple two-dimensional case, cannot be too steep. And this is essentially, oh, by the way, I haven't told you how to actually find these things, but that's, I think, also a nice exercise. Essentially, if this, you can kind of say, okay, if one of these things is not satisfied, then you can either like swap the vectors around in this case, or you can kind of subtract some multiples of B1 from B2 in this case to make it satisfy, and if you can also show that this actually finishes and is efficient. Okay, so that's what we call Lagrange reduction. Now, from this we're going to build the LLL algorithm, and we define an LLL reduced basis by saying that if any of these, and I have to explain it a bit more, but these projected rank 2 sublattices, if these are all Lagrange reduced. And so what is this? Well, we take our ith basis vector and our I+1 the basis vector, and we project them away from the first I-1 basis vectors. So this is a rank 2 lattice because it's just spanned by these two vectors. And if you work out the math, what you get is that in terms of the Gram-Schmidt norm, is that we get this kind of local inequality that we saw in the Lagrange reduction here. So because this local thing is Lagrange reduced, we get this also the same condition on these local Gram-Schmidt vectors. And of course from this we get that the whole profile cannot decrease too slowly, because in every step it can only decrease by a little bit. So we kind of get this, this bound on how steep the thing can be. And from this, if you have a bound on the steepness, and because you also know that the product of these Gram-Schmidt vectors is equal to the volume of the lattice, from that you can actually get a bound on the first vector in your reduced basis. And note that this is like an exponential approximation compared to the normalized volume, so that's kind of exponentially bigger than what the Minkowski bound or the Gaussian heuristic would say. So what's then the algorithm is to actually achieve this? It's kind of extremely simple. Suppose one of these local two-dimensional lattices is not Lagrange reduced, then we just Lagrange reduce it. That's it, sounds simple. The hard part is actually showing that this terminates in polynomial time. Because if it terminates, then we know that it satisfies the definition, but will that do that quickly enough? And that was kind of the big breakthrough when this algorithm got invented. And yeah, it's a really nice proof once you to get into. And for this thing to run polynomial time, we kind of need to slightly relax this Lagrange reduction. Like we need, again, add some epsilon somewhere. And then actually it works by showing that we take this quantity called the potential of a basis, which just depends on these Gram-Schmidt norms. And you can actually show that at each step, every Lagrange reduction you do locally improves this, like decreases this potential. I can very quickly give you intuition. So if you make this local change, then the real span of this thing is the same. Like you only reduce that local basis. So the Gram-Schmidt norms that are behind it, like they don't change at all, and the Gram-Schmidt norms before it also don't change at all, because we only change later basis vectors. So what you have to show is that just kind of the improvement you get locally is enough to decrease this potential, and then because this thing is also lower bounded, can show that this terminates in a polynomial amount of steps. Okay, so we have seen that if we can solve the source vector problem in 2 dimensions, then we can get some kind of reduction algorithm on the faulting. And the BKC algorithm is a simple kind of generalization of this. Now we're not going to look at these 2-dimensional things, but we're going to look at larger dimensional projected sublattices. To be precise, we're going to look at like blocks of size some beta. And what we're going to do in every one of these blocks, so what you normally do is you start on the left and you kind of shift your thing to the right, is we are going to find a shortest vector in this beta-dimensional lattice, and that's where you use like lattice sieving and algorithms like that. And once we find a short vector, we kind of insert it somehow into our basis. So we push this first, we make this first basis vector in this correct sublattice smaller, which means that we kind of push this profile down a bit there. And then of course the rest of the profile changes, but if we keep like repeating this and kind of keep going over this with these blocks and doing that, eventually this thing will be better reduced.
Earlier you said if the next vector is bigger, then you swap them. So why isn't this monotonically decreasing?
So that's like in the 2-dimensional case. There you either swap them or you kind of subtract one from the other. But I mean it's not so simple in the higher dimensional case. But what was the precise question? Like why this does not?
Why is this not monotonically decreasing? So why is it? Does it go up sometimes?
So the thing is, if I push this down, because kind of the volume of this predicted sublattice is the same, the other things in the profile kind of have to increase because the area under it must be the same. So you kind of get this thing where you try to smash things down and other things they are kind of popping up again. And to control that can be quite hard, but in the LL case, you control it precisely by showing that this potential decreases. But yeah.
So basically, this is just another way to look at it as a factorization problem. Like if you decrease one of the factors, another factor must go up, right?
In the sense of like you have this product that's fixed, and I wouldn't. When you mean factorization, you don't mean like prime factorization, or okay. Okay, and actually what you can show is that the higher this block size is, the larger you make these SCP calls, the less steep this profile is going to be. So here we have like a low, here we have, because the block size 10, 20, 30, you see it kind of becomes less steep. And for random lattices, or at least things that behave like random, which is often what we want in cryptography. When we get a public basis, we kind of don't know more about this lattice than that it behaves like random. Then these algorithms are quite well understood. And I mean, you already kind of saw it, I guess, that you get these kind of straight lines in your plot. And this is what we also call the geometric series assumption. And when I say well understood, we can actually, given some lattice dimension, some volume, some block size, we can very precisely say what this shape is going to be. Okay, and this actually gives you this trade-off, because in the full trade-off in this asymptotic curve, because if we would solve SCP in the whole thing with beta equal to the dimension, then we get our exact solution. If we solve it with beta equal to 2, which is LL, we get PKZ with beta 2 is kind of LL. And if we kind of change our beta between 2 and the full dimension, we get precisely this asymptotic trade-off. Okay, so let's give a very short recap and then head to some coffee. We have seen that the source vector problem can be solved in 2 to the 0.292 times the dimension with lattice sieving. Lattice reduction is nothing more than just flattening this basic profile. The LL algorithm gives you, because we can solve SV in rank 2, gives you a way to efficiently get an exponential approximation factor. With BKZ, if we invest some more energy in finding these short factors in larger beta dimensional lattices, we can decrease this approximation factor. And yeah, I didn't mention this, but the same algorithms also are effective in actually finding these unusually short factors, for example, these promise variants of the clone. Okay, then about the whole part 1, we have discussed this basic lattice theory and the hard problems. And we have seen, at least intuitively, how these hard problems can be used for cryptography. And we have seen the best known algorithms to solve these problems, lattice sealing and BKZ. So what's next? Well, this key generation, we have to get into what families of lattices will we use, and how do we generate such a lattice along with a good basis. Why do we trust these lattices? And this is where these kind of average case, or worst case, average case reductions come in. And how do we get more efficiency? Like how do we turn it into very efficient schemes? And that's where we want to add some extra structure, and we will talk about algebraic lattices. Okay, thank you for listening, and enjoy the coffee.